Hi everyone, I decided to make a video going over implicit differentiation because a lot of people were absent that day and some of you just needed more practice on it. So I thought we'd go over what we did in class that day. So we started with a little bit of a review from geometry. I gave a graph of a circle that was graphed on Desmos, and the question said to find the slope of the circle at the point 3,4. So I plotted the point 3,4. By the slope of the circle, it really means the slope of the line that's tangent to the circle at the point 3,4. So what I refreshed everybody's memory on is in geometry, you may or may not have learned that the radius is always perpendicular to the tangent at the line of tangents, at the point of tangency. So if you find the slope of the radius, which is up 4/3, the tangent line should be perpendicular, so its slope is the opposite reciprocal. So the slope of the tangent line should be -3/4. So then I taught everybody some calculus of how we could find that same slope, but in a different way, because even if it's a different subject, all math is the same. So if we got -3/4 using geometry, then we should get -3/4 using calculus. So the first thing that we did was we rewrote the circle equation. X squared plus y squared equals 25. And I said if we want to find the slope of the tangent line, what we have learned this year is the slope of the tangent line is the derivative. I asked everybody what was different about this problem compared to other problems that we have found the derivative for. And people mentioned that there were two variables in this one, and that's what made it different. So I had to change up my notation a little bit. So we've talked a little bit about this notation being the verb of taking the derivative. So I said, let's take the derivative of each piece at a time. Take the derivative of x squared, take the derivative of y squared, and take the derivative of 25. And then I told everybody there's two of these things that you actually already know how to find the derivative of. The only one that's different is the y squared one. So we'll find the derivative of x squared. It's 2x using the power rule. We'll find the derivative of 25. 25 is a constant, so its derivative is 0. So the only one that's new is finding the derivative of y squared, and it's because there's a variable mismatch. So we're finding the derivative with relation to x, but it's a y squared. So what we really have to do is find the derivative of y squared and use the chain rule for the derivative of y part. So the derivative of y squared is 2y, and then the chain rule says you multiply by the derivative of the inner part, which is y. So the derivative of y is dy dx. So what we can do is we can solve for dy dx, and that will give us the slope of the tangent line. So I'm going to do just some old like algebra 1 solving. I'm trying to isolate dy dx, so I'm going to subtract 2x from both sides. So I'm left with 2y dy dx. 0 minus 2x is -2x. And then I'll divide both sides by 2y to isolate the dy dx. So dy dx is -2x over 2y. That's actually the formula for the slope of the tangent line at any point. I gave you a specific point 3,4, so we can plug the point 3,4 into that derivative formula. So here's what that notation would look like. The derivative at 3,4 is, and then we can just plug in 3 for x and 4 for y. -2 times 3, 2 times 4 is -6/8. If we simplify that, we should notice that yes, in fact, we did get the same answer using calculus that we got using geometry. If you look above at part A, we got -3/4 as the slope of our tangent line using geometry, and now we get the slope of the tangent line using calculus. So that part with the dy dx was the new part. So what we did next was we backtracked a little bit and we said, when do we need to use this implicit differentiation and when do we not need to use it? So example number 2, we don't need to use implicit differentiation because the variables all match up. It says find d dx of x squared and d dt of stuff with a t in it and d dy of stuff with a y in it. So the variables match up. So instead of implicit differentiation, you don't see this term much, but you could call it explicit differentiation. So this is what we've been doing. So the derivative of x squared is 2x. Done. The derivative of t to the -5th plus 2t, we use our power rule, -5t to the -6th plus 2, done. The derivative of y is just 1. So when the variables match up, we can just take the derivative the way that we've been taking the derivative all along. It's when the variables don't match up that we need this new dy dx part. So this says d dx of y squared. The variables don't match up, so we find the derivative of y squared, which is 2y, and then we have to multiply by the derivative of y, which is dy dx. The next one, the derivative of sine y, is cosine y, but because the variables don't match up, we need to multiply by the derivative of y. And then the last one, there's a little bit of chain rule. So the derivative of sine of y squared is cosine of y squared. But then the derivative of y squared is actually what we did in part A. It's 2y dy dx. So the key for this is always check to see if the variables match up. If they do, then we take the derivative the way that we have been all along. And if they don't, then we do our new implicit differentiation. Okay, let's move on to another one with a visual. So it says first, estimate the slope of the tangent line. So I noticed that this piece of the graph is really pretty linear. And I counted the rise over run, and it looks a lot like a slope of up 1 over 2. So then we're going to use the calculus and see if the slope really is 1 over 2. So we're going to take the derivative. So I'm going to use my verb of taking the derivative of each piece in my equation. So I'm going to take the derivative of y. I'm going to take the derivative of sine of y. And then I'm going to take the derivative of x. So the derivative of y is 1, but then we need our dy dx because there's a variable mismatch. The derivative of sine y is cosine y, but we need the dy dx because there's a variable mismatch. But then for the derivative of x, the variables do match up, so it's just 1, and I don't need the dy dx part. At this point, we can decide to either solve for dy dx or we could plug in our point. So for this one, I plugged in the point now, and for part C, I solved for dy dx. You could really do it in any order. But let's plug in the point. So I'm going to keep 1 dy dx equals cosine pi, because that's my y value, times dy dx plus 1. Let me draw a little unit circle off to the side. The cosine of pi is -1. So I have 1 dy dx equals -1 dy dx plus 1. I'm going to move that over here. 1 dy dx equals -1 dy dx plus 1. So I want to make sure to get all the dy dx's over to the same side. So I'm going to go plus 1 dy dx plus 1 dy dx, which makes a grand total of 2 dy dx equals 1, and then I divide both sides by 2, and sure enough, that's what our estimate was. We said, that looks like a slope of 1/2, and then we do the calculus and we get 1/2. So that's the derivative of the tangent line at that particular point. If we just want a formula for the derivative for the slope of the tangent line at any point, I'm going to go back to the green part, 1 dy dx, cosine y dy dx plus 1. And at this point, we would solve for dy dx. So we have to get all of our dy dx's over to the same side. So cosine y dy dx, I'm going to subtract that from both sides. So I get 1 dy dx minus cosine y dy dx equals 1. And then do you see that the 1 dy dx and the cosine y dy dx have dy dx in common? So we can factor that out. Dy dx times 1 minus cosine y equals 1. And then in order to solve for dy dx, you would divide both sides by 1 minus cosine y. I'm kind of running out of room, so I'm going to move over here to do that. It was at dy dx times 1 minus cosine y equals 1. So I just divide both sides by 1 minus cosine y. So that's a formula for the derivative at any point. The slope of the tangent line at any point. All right, let's do one more example together. Implicit versus explicit differentiation. When do we need to do the implicit and when don't we? So example A, the variables match up, so we don't need to do our new implicit differentiation. We just find the derivative and we have to use the chain rule. So this, I like to rewrite these as sine of t cubed plus 1 squared. I think it's so much easier to see what we're doing. So the derivative is, I'm going to use the chain rule. So I need to do the power rule first. I'm going to need to do the something squared part. So I'm going to move the 2 in the front, and then sine t cubed plus 1, just to the first power, times the derivative of what's inside. So the derivative of sine is cosine. And then the derivative of t cubed is 3t squared. So that's my final answer for that one. So that's old stuff. I mean, not very old. We just basically learned it, but not the implicit differentiation. The difference in part B is there's two variables. So if we find dy dx, we're finding the derivative with respect to x, but there's a y in there also. So we need to find the derivative of each term. So I'm going to put my notation in there where I say find the derivative of x squared, find the derivative of y squared, find the derivative of 25x, and find the derivative of y. So the derivative of x squared is just 2x. The derivative of y cubed is 3y squared, but there's a variable mismatch, so we need dy dx. The derivative of 25x is just 25. And then the derivative of y is just 1, but there's a variable mismatch, so we need dy dx. At this point, just like the last problem that we did, I want to get all the dy dx's over to the same side. So I'm going to subtract 1 dy dx on both sides. But then I still have the 2x over to the left. I really want to move that over to the right also. I would like all the dy dx's on one side and everything else over on the other side. So I'm going to go minus 2x over on the other side. If you don't want to do the extra step of having to factor out the dy dx, I could actually right now just put the dy dx in front and then put 3y squared minus 1. So if I want to save a step, instead of writing 3y squared dy dx minus 1 dy dx, I can take the dy dx out now. And then on the right, it will be 25 minus 2x. And then you divide both sides by 3y squared minus 1. And that is your answer for dy dx. So hopefully this is helpful if you missed class or if you needed to see it one more time. I'm sure that if you Google implicit differentiation examples or something like that, I'm sure that you can find a bunch of examples and a bunch of videos on the internet. But hopefully this will be a good start. See you in class. Bye.